Hi everyone. So in this video, we're going to be talking about a specific important example of an exponential function, which is f of x is equal to e to the x. So this is sometimes referred to as the natural exponential function. And e, we'll see, is basically just a very special number. It's kind of like pi. It's a number that, it's just a number, but it has some special properties. So we're going to be spending most of this video actually talking about that number e and what it is and how it's defined. And then we'll talk about what the exponential function e to the x looks like. So in order to understand what the number e is, we need to talk a little bit about two different types of numbers. So this is something we actually did talk a little bit about earlier in the quarter when we were discussing rational functions. We talked about what rational numbers are, right? So we said that a rational number is a number that can be written as a ratio, right? Rational has the word ratio in it. So a rational number is basically a fraction. So a rational number is a number that can be written as p over q, where p and q are whole numbers. So I'll write down some examples of rational numbers in just a second, but one other important thing to know about rational numbers is that when you write a rational number as a decimal, so when written in decimal form, a rational number will have either finitely many, and I'll explain what I mean by that in a moment, decimal places, or if it has infinitely many, they'll repeat with a pattern. So infinitely many decimal places that repeat in a pattern. Okay, so let's just write down some examples of rational numbers and we'll see how they kind of fit this description. So one example of a rational number would be the number 3/4, or actually let's say 5/4 to make it a little bit more interesting. So 5 over 4 is a rational number, right? It can be written as a fraction. So what would 5/4 be in its decimal form? 5/4 would be 1.25. So when I say finitely many decimal places, I mean there's only two, right? Here we have 1.25. So a rational number could have a lot of decimal places, but it's always going to stop at some point. Or it will repeat with a pattern. So just to give an example of one that is a little different, another example of a rational number would be 2/3. So what makes 2/3 a little bit different is that if you write it as a decimal, if you type it into your calculator 2/3, it's going to tell you 0.6666666, and it just keeps going. And so when I say infinitely many repeating with a pattern, this is an example of that, right? It's a very simple pattern. It's a pattern where it just repeats the same number. There are other rational numbers where maybe it goes 1 2 1 2 1 2 1 2, or 5 6 7 8 1 5 6 7 8 1 5 6 7 8 1. Anything that repeats with a pattern is always going to be a rational number. Okay, so what is the kind of opposite of a rational number? Well, that's an irrational number. So an irrational number it cannot be written as a fraction. And then the thing that's going to be really important in this video, or for understanding what irrational numbers look like, is that they have infinitely many decimals, and those decimals don't repeat with any specific pattern. It's, I hesitate to say random, but if you just looked at the decimal places, it would seem really random. It just kind of keeps going and going and going with all sorts of different numbers. So let me kind of write that down. So when written as a decimal, or when written in decimal form, an irrational number has infinitely many decimal places, and then, as we said, the important thing is that not only that it's infinitely many, it's that they're repeating without a pattern. Okay, so when you hear infinitely many decimal places repeating without a pattern, there might be a number that kind of pops into your head that's really famous for that, right? So what's a famous number that has infinitely many decimal places that repeat without a pattern? Pi, right? Pi might be like the first number you think of that fits this description. So pi is an irrational number. So, people spend their lives trying to memorize decimals of pi because it has these infinitely many decimals that just keep going and going and going and going. I'm not one of those people. I don't know. I think I only know 5 digits or something of pi. So the decimal approximation that we commonly use is we would say pi is approximately equal to 3.14, right? That's going to be good enough for most calculations that you need to do. However, 3.14 is not exactly what pi equals, right? Pi goes on forever. It has so many different digits. And so even though we can say that pi is approximately equal to 3.14, when we want to be exact, we have to just write the symbol pi. So, but when we need to be exact, we must just write down or use literally the symbol pi. So this goes back to, you might have heard me say in this class, exact form, write your answer in exact form. That means that you're not doing any approximation. And so the thing with irrational numbers is because they have infinitely many decimal places, there's no way to actually write down the number in its exact form, except for by writing this symbol, right? So it's this is kind of a weird concept, but the idea is that this symbol represents a number that is impossible to capture by writing down. So instead of trying to, write down hundreds of decimal places and still not having the exact form, you just write the symbol pi. Another example that we've come across in this class, with using the quadratic formula would be the square root of 2. So the square root of 2 is an irrational number. If you wanted to approximate it, if you type it into your calculator, you'll see that it's approximately 1.41. But that's not exactly its value, right? When we want to be exact, we just have to write down square root of 2. Anything else, any kind of, you can even write down thousands of decimal places and it's still not going to be exactly that value of that number because it has infinitely many decimal places. There's no way to actually write it down, so we just write this kind of symbol to represent the number. So that's why when we're doing the quadratic formula, if I tell you, keep your answer in exact form, you write square root of 2. You don't type it into a calculator. Okay, so why are we talking about these numbers? Well, E, which is the number we're going to be focusing on in this video, it basically fits into this category. It's another irrational number. So the number E, so that's what we'll be talking about on this page, is an irrational number. So what is the approximate value of E? Well, E is approximately equal to 2.72. So just like how, you might want to know off the top of your head, okay, pi is about 3.14. Same thing with e. You want to know that e is about 2.72. However, just like with pi, that is not actually an accurate representation of e. So I found this website that actually lists out the first 2 million digits of e. So I just want to show you, just to like really convince you that e is approximately 2.72, but that's not its actual value. So if you look here, it says e is equal to, and you can see it says 2.718, right? So that abbreviates, or that rounds to 2.72. But this is this page where it just, like, if you look at the bar on the right, like, look how little I'm scrolling, and it's still more and more digits of e, right? I can scroll this down and down and down, and it just keeps going. And this isn't even the whole number, right? So when I say it has infinitely many decimal places, I mean it. And that's why we have to use this symbol. That's why we just write the symbol e, because who can write down all of these digits when there's infinitely many? So the main important thing, like I said, that I want you to know about e is that, again, it's just a number. It's a special number, but it's just a number, and that it's approximately equal to 2.72. I do want to tell you what's called the precise definition of e. So this is going to be a little bit funny. It's not a way that you're probably used to thinking about numbers, but I do want to tell it to you because it feels a little wrong not to. Okay, so how can we like precisely define e? I just showed you a page that has 2 million digits, but that's still not even the exact value of e, right? It's still an approximation in some sense. And so it turns out that we have a nice way of defining e, and it actually has to do with end behavior. So if you take the expression 1 plus 1 over n to the nth power. So if you take this expression and you take n and make it bigger and bigger, so as n approaches infinity, right? We talked about this with n behavior. If we say as n approaches infinity, that means that we're going to be looking at this expression and we're going to be thinking about what happens when n gets bigger and bigger and bigger. So as n approaches infinity, this expression here, that actually approaches the number e. I know this is probably a weird, like strange definition. I want to show you a little bit of how this would work just to kind of convince you. So how would we, like thinking back to when we first talked about n behavior, without looking at the graph or a graph of something, how can we kind of get an idea of what the end behavior of something is? Well, we can plug in numbers, right? So we can do, for example, 1 plus 1 over 10 to the 10th. And then we can do 1 plus 1 over 100 to the 100th. And then we can do 1 plus 1 over 1,000 to the 1,000th. And see what each of these gives us. And what we'll see is that as we increase this value of n, these numbers are going to get closer and closer to about 2.72, which is e. Okay, so if you were to type this into a calculator, what is 1 plus 1 over 10? Well, that would be 1.1 to the 10th, right? And I want to pause for a second because I think this is kind of interesting. Personally, if I had to guess what 1.1 to the 10th is, I would probably think it would be pretty close to 1, right? If you multiply 1 by itself over and over, it keeps being 1. So I would kind of think that 1.1 wouldn't get that much bigger. But it actually does. So if you take 1.1 and raise that to the 10th power, so if you multiply it by itself 10 times, you actually get 2.59 approximately. Okay, so what about this next one? So this next one would be 1.01 to the 100th. So it's kind of interesting because now the number that we're using as our base is even smaller, even closer to 1. But we're now multiplying it with itself a bunch more times. And so if you type this into a calculator, what you'll find is that this is approximately 2.70. And now if you do the same thing with 1,000, so that's now 1.001 to the 1,000th power. So now you're taking this number that is really, really close to 1 and multiplying it with itself 1,000 times, you'll find that it's approximately 2.72, which is getting really close to e. And so the idea is that if you kind of keep pushing this, so if you do the 10,000th, the 100,000th, the 1,000,000th, the billionth, the trillionth, as you keep increasing this value of n, your outputs are going to get closer and closer to the actual value of e. So again, I know this is a little weird. I know it's probably a little confusing. If you didn't totally follow this, I just want to let you know that that's okay. If you didn't completely follow this, you're going to be fine. Really, all you need to know for this class is that e is approximately equal to 2.72. That's really what I need you to know in order to succeed in understanding what the exponential function e to the x looks like. So now I want to talk about what the graph of f of x is equal to e to the x looks like. So even without plotting points, eventually we're going to plot points, but I first just want to think, without plotting any points, can we get a general idea of what the shape of this graph is going to look like? So remember that we already know that exponential functions, they only have two shapes, right? They're either going to look like this, or they're going to look like this, right? Those are the only two options for exponential functions. And so how do we decide which way it looks? It just depends on what that base is, right? And so the base, we need to look at whether the base is bigger than 1 or less than 1. So e, we just learned on the other page that e is approximately 2.72. So what does that tell us? Well, it tells us that this function should have a shape that will look kind of like this. So again, I know e, like in some ways it's a special number, and we just kind of are getting used to it, but at the end of the day, it's just a number. So because we know it's approximately equal to 2.72, that gives us a good idea of what this graph is going to look like. But let's try to get a little bit more specific. So let's fill out a table with some values for this function so that we can sketch its graph a little more accurately. Okay, so I just want to do a few points. For the negative inputs, we'll just kind of use our knowledge of what the asymptote looks like rather than dealing with plugging in the negative numbers. So, okay, first thing we have is 0. So e to the 0. So what is e to the 0 going to equal? Well, again, e is just a number. E is a number, and like any other number, any number to the 0 is always going to be 1. So we already know that our graph, just like every other exponential function, has a y-intercept of 0, 1. Okay, what about when we plug in 1? Well, e to the 1, any number raised to the first power is just itself, right? So it's e, and we know that e is approximately 2.72. So if we go and plot that point, that's going to be 1 and then approximately 2.72, something like that. And then what about when we plug in 2? Well, that's e squared. And if you type that into a calculator, you'll get approximately, I guess I only did it to 1 decimal, so sorry for the inconsistency, but it's approximately 7.4. So that's going to be somewhere like here. So the right side is going to look like this. And then the left side, as we said, it's going to have a horizontal asymptote, just like any other exponential function. So basically, everything that we learned about exponential functions in the first video about exponential functions applies to e to the x. So let's write down some of those things. Even though we kind of know that they're already true for all exponential functions, I just really want to emphasize them here. So I want to talk about the domain, the range, the y-intercept, and the horizontal asymptote, just to kind of have them all written down. Because even though e to the x is just another exponential function, it is really important. So it's going to come up a whole lot in calculus. So it's just really important that you're very familiar with how the graph looks and some of the kind of basic information about the graph. Okay, so what is the domain? Well, just like with any exponential function, you can plug in any number, right? You can raise e to whatever number you want. So the domain is all real numbers. We can also see that the graph just continues to the left, continues to the right. So there's no issues with the domain. So the range, well, the range, we can see the graph keeps going up and up and up. So the y values are going to get higher and higher as we go, but the y values are never going to be less than 0. And so that tells us that the range is 0 to infinity, not including 0, because the graph will never actually touch the x-axis. The y-intercept, as we already discussed, is the point 0, 1, because e to the 0 is equal to 1. And then the horizontal asymptote, as we saw on the graph, is the line y is equal to 0. One other thing I just want to show you to kind of give you a little bit more of an idea of what the shape of this graph looks like. So remember that the bigger the base is of an exponential function, the steeper its graph is, right? So here I have 2 to the x in green, and then I have 3 to the x in red. So I want you to think about, where is the graph of e to the x going to fit in? Like, if you had to guess, like, where in this picture the graph of e to the x is going to be, where would it be? Where, like, on which side of these different functions is it going to lie, and which one is it going to be closest to? Well, it should be between 2 and 3 to the x, right? So here's 2 to the x, here's 3 to the x. E to the x should be between them, because 2.7 or 2.72 is between 2 and 3. Now, which one should it be closer to? Well, 2.72 is closer to 3 than it is to 2. So we should expect to see the graph be a little closer to the red function. So let me graph e to the x. And so we can see that, yeah, it is closer to the red function, but it lies between the green and the red function. So that gives you a kind of another idea of just the general shape of the graph of e to the x. Okay, last thing I want to do is I just want to graph a couple of transformations of e to the x, just to get a little bit more practice. So the first one that we're going to do is e to the negative x plus 1. Okay, so what is this graph going to look like? Well, we have a couple of different transformations going on, right? So the first thing that's going on is that we have we're negating the x. And so we know that if we apply a negative sign, it's going to be a reflection. And in this case, it's specifically going to be a reflection over the y-axis, right? It's a horizontal reflection. And then what about this plus 1? Well, that's going to be a shift, right? And it's specifically, because it's being added to the function as a whole, it's going to be a vertical shift. Okay, so how do we go about graphing this? Well, we can just take our kind of few key points, and honestly, it's probably even enough just to focus on these 2 points here. And then as long as we just know how the graph continues to the left and continues to the right, we'll be able to sketch it. Okay, so first thing we're doing is we're reflecting the graph over the y-axis. So let's do this in steps. Let's start by doing the reflection over the y-axis. So when we reflect over the y-axis, the point that was at 0, 1 is still going to be there, right? It's not going to change. The point that was originally at 1e is now going to be at negative 1e. So it's going to be somewhere like this. And then we had a point at negative 2e squared, or at 2e squared, so that was around 7.4. Now we have negative 2e squared, so we have a point here. And so this would be the graph of just doing that, that horizontal reflection, right? And we still have a horizontal asymptote, it's just now happening to the right. So this would be just e to the negative x. Okay, next thing we want to do is we want to shift this graph up by 1. And so that means that every y coordinate needs to get 1 added to it. So we have this point moving up here, the y-intercept, and then the point that used to be at e will now be at e plus 1. So that will be about 3.72. And then the point that used to be at e squared will be at e squared plus 1. So that's about 8.4 instead of 7.4. And then what about the horizontal asymptote? Well, if we shifted everything up by 1, that means that our horizontal asymptote should now be at y is equal to 1. And so our graph is going to look something like this. So I'll just label this. This is our final graph. Okay, one other transformation I want to do is let's graph g of x is equal to negative e to the x plus 2. Okay, so what's going on with this function? Well, we now have a negative sign, now not on the x, but on the whole function. And so when you have a negative sign on the whole function, that's a vertical reflection, or a reflection over the x-axis. And then what about adding 2 to x? Well, that's going to be a horizontal shift. And specifically, if we're adding 2 to x, that's going to be a shift to the left. Okay, so let's start sketching this. And again, let's do this in 2 pieces just to kind of make it a little easier to deal with. So the first thing we want to do is we want to reflect the graph over the x-axis. So that means that we're going to take our key points and we're going to change their y-coordinates to being negative. So originally we had a point at 0, 1, that's now going to be at 0, negative 1. We had a point at 1e, that's now going to be at 1, negative e, so that's negative 2.72 approximately. And then we had 2e squared, that's now going to be 2, negative e squared, so that's about negative 7.4. And then the graph is going to have still this horizontal asymptote, it's just now approaching it from the other side. And the graph will go down like this. So this would be the graph of y is equal to negative e to the x. But then we want to shift this graph to the left by 2. And so all that means is just taking all of our x coordinates of these key points and just moving them to the left by 2. So this point that was originally our y-intercept is now going to be here. The point that was at 1, negative e is now going to be at negative 1, negative e. Just moving that over by 2. And then the point that was at 2, negative e squared will now be at 0, negative e squared, so negative about 7.4. And so the graph is going to look like this on the right side of it. And then what is the left side going to look like? Well, it's still going to have that same horizontal asymptote. It's just, again, picture that you're taking that green graph and you're just sliding it to the left. So it's still going to have the same horizontal asymptote. It's going to kind of approach it in a slightly different way. But it's still going to have a horizontal asymptote at y is equal to 0. All right, so that is it for this video. As I said, really the main takeaways I want you to have from this are just an understanding of what the general shape of e to the x looks like, a knowledge that e to the x, or that e is just a number, it's an irrational number, it's approximately equal to 2.72. Those are really the most important takeaways from this video. All right, I'll see you all in our next video.